proceed to the effective or RMS value. So the idea of effective value arises from the need to measure the effectiveness of a voltage or current in delivering power to a resistive load. So the effective value of a periodic current is the DC current that delivers the same average power to a resistor as the periodic current. So for example, if you have an AC circuit shown in figure A and we have a DC circuit shown in figure B, so it says that the effective value of a periodic current or voltage is the DC current or voltage that delivers the same average power to a resistor as the periodic current. For an average power of an AC circuit, this is given by this equation. DC circuit, our power is I squared times R, where our I is this effective current. So equating the two equations, uh, R over T integral of I squared dt from 0 to t, just equivalent to I effective squared times R. Now solving for our I effective, just equal to square root of 1 over t integral of I squared dt evaluated from 0 to t. The effective value is also called the RMS value. The same with voltage, equivalent to 1 over t integral of v squared dt evaluated from 0 to t. This is also equivalent to our VRMS. So the general equation for the effective or RMS value for any periodic function x of t is given by this equation. So the effective value of the periodic signal is its root mean square, or the RMS. So to find the RMS value of x of t, first we need to find its square, the square of x, and then find the mean. So finding the mean, we integrate the square of x over one period, this one, and then we get the square root of that mean. So that's why it's called the root mean square. So the effective value or RMS values of the sinusoidal current and V. Now for the sinusoidal current, we have using trigonometric identity, Im squared is just constant, so this is Im squared over t. Then substituting cosine squared omega t with an identity, we have 1/2 times 1 plus cosine 2 omega t dt. So we all know when we integrate a cosine function or a sine function over one period, it is just equivalent to 0. So we are left with this equation, m squared over 2t integral of dt from 0 to t. So our IRMS is equivalent to Im over square root of 2. Or our Im is equivalent to square root of 2 IRMS. Same with voltage, VRMS is equal to Vm over square root of 2. Or our Vm is just equivalent to square root of 2 VRMS. Looking at the average power, So the average power is given by this equation. Now using the RMS values for I and V, we have 1 half times square root of 2 VRMS times square root of 2 IRMS times cosine of theta V minus theta I is equivalent to VRMS times IRMS times cosine of theta V minus theta I. So we have our equation for an average power using VRMS and IRMS. So for an example of an RMS value, if you measure the voltage in our AC sockets, we measure the VRMS. So when we measure 230 volts in our AC sockets, that means that our VRMS is equivalent to 230. So next, we'll introduce the apparent power and power factor. So the product VRMS and IRMS is known as the apparent power. It is denoted by S. So not to confuse it with the average power, it is given a unit of volt ampere or VA. So our average power can be expressed in the apparent power times the cosine of theta V minus theta I. So the angle theta V minus theta I is called the power factor angle, since it is the angle whose cosine is the power factor. So meaning this cosine of theta V minus theta I is our power factor. Or the power factor is just the ratio of the average power to the apparent power. So it has no unit. Our PF is just equivalent to P over S, or equal to cosine of theta V minus theta I. Now the power factor angle is equal to the angle of the load impedance if V is the voltage across the load and I is the current through it. So if this is the voltage across the load and I the current through it, says that the power factor angle is just equivalent to the load impedance angle. So our ZL is equivalent to V over I, or in terms of our VRMS angle of theta V over IRMS angle of theta I, equal to, we have magnitude Z angle of theta V minus angle theta I. So this angle is just the power factor angle or the angle of the load impedance, d theta. So the load impedance d theta can either be positive or negative depending on the type of load. So if we have an inductive load, our z theta is positive, and if we have a capacitive load, our theta is negative. So for example, if we have a voltage with a magnitude of V angle 0, and then Z, we have Z angle theta Z, or inductive. So plotting them in the phasor diagram, if this is our Z, angle theta Z, and this is our V, our I is lagging. So our current lags the voltage by the angle of negative theta z. Now for the second case, we have a capacitive load C angle of negative z, and plotting them in the phasor diagram. This is our z angle of negative theta z. This is our voltage. For current leads the voltage at the angle of positive theta z. So for example, a series connected load draws a current of 4 cosine 100 pi t plus 10 degrees amperes when the applied voltage is 120 cosine of 100 pi t minus 20 degrees volts. So find the apparent power and the power factor of the load, and then determine the element values that form the series connected load. So getting the RMS values of the current and voltage, IRMS equivalent to 4 square root of 2 angle of 10. Our VRMS equivalent to 120 over square root of 2 angle of negative 20. So looking at the angles of the voltage and current, clearly we can see that the current is leading the voltage. If we plot the phasor diagram, this is our voltage angle of negative 20 degrees. This is our current angle of 10 degrees. The difference between the voltage angle and the current angle equivalent to negative 20 minus 10. We have negative 30. So this should be our theta z. So meaning our load is capacitive. So solving for the apparent power, we have magnitude of VRMS times IRMS. We have 120 over square root of 2 times 4 over square root of 2. We have 240 volt amperes. Now the PF equivalent to cosine of omega V minus omega I is equivalent to negative 30. So cosine of negative 30 is equivalent to 0.866. Now since our PF has no unit, and then if we get the cosine of positive or negative 30, it's just equivalent to 0.8666. We need to indicate if it is leading or lagging. So if the power factor angle is positive, meaning the current is lagging. Or if the power factor angle is negative, the current is leading. In this case, our power factor angle is negative. In this case, it is leading. So our Z is equivalent to VRMS over IRMS equal to 55.98 minus 315, or this is just equivalent to 30 angle negative 30 ohms. So our load is positive. For our next example, calculate the power factor of the entire circuit as seen by the source. And then what is the average power supplied by the source? So to get the power factor as seen by the source, we need to get the equivalent impedance as seen by the source. DEQ is equivalent to 8 minus J6 parallel with 4, then with series with 10. So this is just equivalent to 202 over 17 plus J76 over 17. So we can see that our load is inductive. In phasor form, this is 12.696 with angle of 20.618. So our PF is equivalent to the cosine of the impedance angle. Cosine of 20.618. So we have 0.936, and this is lagging. On getting the average power, we have P equal to magnitude of VRMS times IRMS. We have cosine of theta V minus theta I. This term is equivalent to our PF. We can express IRMS in terms of voltage over the impedance. So our average power becomes VRMS squared over magnitude of ZEQ times PF is equal to 2007.14 watts. Or we can always get the current is equivalent to 165 angle 0 over our ZEQ. We have 12.997 with angle of negative 20.618 degrees. So clearly, plotting the phasor diagram, if this is our V, our current is lagging. Is negative 20.618. So getting the average power using VRMS and IRMS, we have 165 times 12.997 times cosine of 0 plus 12.618, just equivalent to 2007.14 watts. Is equal to